Hi there, and welcome to the fourth video on the topic of graphs and transformations for the Year 12 portion of the A-level course. This lesson we're going to be having a look at translating graphs and functions, and the warm-up questions which we have every time are going to tie into the main bit of this lesson. So do pay attention to the lessons from the warm-up, because this warm-up is going to be very relevant to what we're going to do after the warm-up. So in terms of me mentioning the warm-up, here it is. 4 questions, almost as ever, so have a go at these, try them first before looking at the video answers, then once you've come to the answers, check them using the video and make any corrections where necessary. So let's have a look at question 1 in a bit more depth. Question 1, we're asked to solve this quadratic equation. Now, luckily, you should be able to spot by now, this factorises quite nicely, and so we can factorise this into x plus 1 x minus 3 equals 0. Okay, two numbers that multiply to minus 3 and add to minus 2 are 1 and negative 3. So therefore, the solutions to this are when the first bracket is equal to 0, in other words when x is minus 1, or when the second bracket is equal to 0, in other words when x is 3. For part B, we've got the same expression, but we need to write this in completed square form. So I'm just going to write it down as is. Now we need to remember when completing the square, we put into brackets, instead of the x squared, just a single x, and we half the coefficient of the x term. So half of minus 2 is minus 1. You then square it all, and minus off this last term squared. So minus 1 all squared is positive 1, so we minus off that 1. So all we've done here is just rewrote x squared minus 2x in this form. Now we subtract the 3, because the 3 was there to begin with. Final step, we can simplify slightly, and we have x minus 1 all squared minus 4. Remember, the completed square form of a quadratic function tells us where the turning point is. So this will have a turning point where x is at 1 and y is minus 4. Question 2, I want you to have a look at this before just tackling it head on. So have a look at what's in the brackets and compare it to question 1. Okay, so from question 1, just to remind you, the function we had was x squared minus 2x minus 3 equals 0. Okay, so let's just compare what we have in question 1 from what we have now in question 2. You should notice it's more or less the same thing. It's got the same characteristic form. The only thing different here is instead of having x as the input, the variable input we had for question 1, now the input is x minus 2. So we did mention function notation in the previous lesson, so we're going to use this here. So I want you to consider that question 1, I know this isn't in the actual question, but it's worth exploring with you, because as I mentioned, it's going to be very useful and a powerful lesson later on. So question 1, we can consider that as just being f of x, where the input was x. So for f of x, we took the input, we squared it, we minused 2 lots of the input, and minus another 3, and we got that that was equal to 0. So this is what the function does. It squares the input, takes away 2 lots of the input, and minuses 3. And so if we have a look at this here, for 2 part A, instead of having an input of x, we've got x minus 2 which has been input, and so f of x minus 2 would be x minus 2 all squared minus 2 lots of x minus 2 minus 3. Okay, in fact we can forget v equals 0, because that's just a particular value of the function. Okay, so we can just compare these expressions for f of x and f of x minus 2. So therefore, question 2, what we're doing now, we're looking at f of x minus 2 if we define f of x as the function from question 1. So anyway, let's solve this the long way. So a bit of expanding to do. So x minus 2 all squared, we need to do that first of all. What we'd have is x squared minus 4x plus 4, then minus 2 times x, so minus 2x's, minus 2 multiplied by minus 2, that's positive 4, then minus 3 equals 0. So let's neaten this up. So we've got x squared minus 4x minus another 2x, that's minus 6x's, and then the constants 4 plus 4 minus 3, 4 plus 4 is 8, minus 3, that's minus 5. Once again, this will nicely factorise. Two numbers that multiply to negative 5 and add up to negative 6, that's minus 1 and minus 5. So we can put this into brackets and say it's the same as x minus 1, x minus 5 equals 0. Therefore, the solutions are when x is 1 and x equals 5. So we change the input to x minus 2 instead of x. So we subtracted 2 from the input. Do you remember the solutions to question 1? Question 2 got 1 and 5. Let's just remind ourselves what we had from question 1 just for a moment. For question 1 we had minus 1 and 3. If we add 2 to both of these, minus 1 becomes 1 and 3 becomes 5. So when we subtract 2 from the input, the roots get added to. So if we subtract 2 from the input, we add 2 to the roots. Is that a coincidence? Does this 2 have something else to do with things? So just bear that in mind. We're going to return to this. For part B, same as one part B, we need to rewrite this in completed square form. So, in other words, we're going to complete the square and find out where the minimum is. So we put the x in brackets, we half the minus 6 to make it minus 3, we square all that, we subtract off this minus 3 squared, minus 3 all squared is 9, so we minus off 9, and then plus 5. So that becomes x minus 3 all squared, and minus 9 plus 5, that is overall minus 4. So the turning point for this one is at 3 minus 4. And again, if I just quickly compare to 1 part B, the turning point for this one was at 1 minus 4. So the turning point's gone from 1 minus 4 to 3 minus 4. So again, that's been moved 2 along the x-axis, as have the roots. So when we've made a change inside the brackets of a minus 2, it seems to added 2 to the x-coordinates. So we're going to explore this lesson. Question 3. Solve x squared minus 2x minus 3 equals minus 4. Again, I'm just going to remind ourselves, if we just think of f of x as being what we had in question 1, which is x squared minus 2x minus 3. And we've got it written here, of course, as well. So here, to solve this, we've got f of x equals minus 4. And so if we add 4 to both sides, what we get here is x squared minus 2x minus 3 plus 4 equals 0. Now let's just think about what this expression is here, which I'm just going to box off. So compare this to f of x. So f of x is this thing here. So this here is f of x plus 4. So what we're solving is the function f of x plus 4. So this plus 4 isn't inside the brackets, It's outside the brackets. So we're solving when is f of x plus 4 equal to 0. Now, we can now simplify this. This will neaten up quite easily. So minus 3 plus 4 is the same as plus 1. Two numbers that multiply together to give us 1 and add up to minus 2, that's minus 1 and minus 1. So this is actually a perfect square. We can say this is x minus 1, brackets x minus 1. In other words, x minus 1 all squared. Therefore, that's just got one repeated root when x is 1. Okay, so when x is 1, y is 0. So the turning point of this is going to be 1, 0. Whereas if you remember the turning point of just f of x, the turning point of f of x was 1 minus 4. This one's going to have a turning point of 1 and 0, which is 4 higher. So by adding 4 to this, it looks like the graph will move 4 higher. Now, in terms of me saying about graphs moving, this is what question 4 is going to try and add a bit more dimension to. So question 4 is going to give a bit more of a visualization of what we've talked about. So question 4, we're going to sketch on f of x, g of x, and h of x accurately on this graph. But before I get going, I'm just going to fill in this graph with some axis labels. Okay, so that's what we have. And so we have f of x. G of x, just to remind you, is what we had from question 2. So g of x, like I said earlier, is f of x minus 2. And h of x is what we solved here, and that was f of x plus 4. Okay, this bit's f of x, and we solve it by adding 4 to the whole thing. And so f of x is almost like the original function. We're going to compare g of x and h of x to our original. So it just says to sketch accurately. Okay, so bear that in mind. So we can use what we had from question 1 to help us. So from question 1, what we had here was the turning point of f of x. So the turning point of f of x we worked out was 1 minus 4. Have a look at your worksheet and just use question 1. So 1 minus 4, this is in red, so I'm going to plot this in red. So the turning point of f of x was here. The roots of it, we worked out, were minus 1 and 3. So we can add those into our plot too. The y-axis intercept, when x is 0, it says sketch accurately, so let's know as much as we can. When x is 0, this becomes 0, take 3. So by substituting in x is 0, we see that the y-axis intercept would be negative 3. Okay? Remembering that quadratics are always symmetrical, that's the turning point. So if that's minus 3 here, on the other side, we'd have 2. We could do with working out what happens when x is 4 as well. So when x is 4, we'd have 4 squared, which is 16. Take away 2 lots of 4. So 16 take away 8 is 8. And take away 3, we'd have 5. And again, by symmetry, that's going to be the same at this end as well. Now, because I'm sketching free graphs, and it says to do it accurately, and if you've watched some of my videos already, by now you'll know my sketching's absolutely bloody useless. I've sort of cheated, so forgive me here, but I'm going to just superimpose one I've made earlier on Desmos onto this plot. But you can see here, you do know how to get these points. It's just a case of smoothly joining these up. I can't join smoothly, sadly. That's one of my many failings, but never mind. So if I just take this here, okay, and move it up, this faint red line, that's f of x. So that's my graph of f of x, the red line. We're now going to do the same for g of x, by again remembering what we had from question 2. So for g of x, which was x minus 2, what we had was roots at 1 and at 5. The turning point of this one, because we had in completed square form it was x minus 3 all squared minus 4, the turning point, the minimum, was x is 3, y is minus 4. So down here is the turning point. And the x-axis intercept, sorry, the y-axis intercept, I mean to say, for this one, if we were to substitute in when x is 0, we'd have 0 minus 0 plus 5. So the intercept for the y-axis is 5. Okay, so you can actually see, just by comparing the red coordinates to these, they've just been shifted 2 along. Okay, that route's moved 2 along, this route's moved 2 along, the turning point's moved 2 along. So if I do these to the other points as well, move that 2 along, they're going to coincide here, move that 2 along, that's going to go here. Finally, this one moved 2 units to the right, would go there. And so in the same way I cheated for f of x, I'm going to cheat now for g of x. Let's bring this graph up and make it fit like so. So we have here that this blue curve is g of x, and just to remind ourselves of what I mentioned earlier, g of x is the same as f of x minus 2. Finally, h of x. So let's remember what we mentioned about h of x earlier. We worked out the turning point by completing the square. The turning point was x minus, well, sorry, we worked out that it was x minus 1 all squared equals 0. So the turning point would be at 1, 0. So the turning point for this one is actually here. Okay, the y-axis intercept, 0 takes 0 plus 1 when we sub in x is 0. So this one would go through 1 here, and at the other side we'd have this here. So then we can substitute in what happens when x is 3, and we can use the symmetry argument like we did for this point. When x is 3, we'd have 3 squared, which is 9, take away 2 lots of 3, 2 lots of 3 is 6, so 9 takes 6 is 3, plus 1 would be 4. So we have 3 and 4, and by symmetry over here, we'd have minus 1 and 4. So let's just bring up this graph to complete the picture. Oops. And this one goes in like such. And so this graph here in the green is h of x, and just to remind ourselves, h of x is f of x plus 4. So just by looking at this here, if f of x is our original, if you like, f of x minus 2, we just shift f of x 2 units in the positive x direction. So the minus 2 almost acts as a plus 2. So when the change in this function, the change happens inside these brackets here, it almost works opposite to what common sense would tell you. Instead of taking away 2, we add 2 in the x direction. But when the change is outside the brackets, like this 4 is on its own, f of x going to f of x plus 4 is a more common sense change. We just literally add 4 to each y coordinate. You can see here from this minimum, the minimum at minus 4 goes up to having a minimum when y is 0. So we're going to explore this in a bit more depth come up with a few more examples, and then generalize our findings later to give you the take-home points which you need to remember and apply for the A level. So let's have a look at some more of these. So when we're translating functions, let's just go on our intuition, what we've discovered so far. So we have this function notation, which we've talked about. That defines the input variable as x, which can vary. So it's sometimes called the independent variable. So x can be whatever it wants to. You can't tell x what to do. However, the y output depends on what you input for it. So y is called the dependent variable because it depends on the input which generates the output. In other words, its value is fixed and determined by the chosen input x value. However, normally because we use x is like the standard unknown letter we use in algebra, it's not the only unknown letter. So it's not just x we could use any symbol in fact to define our independent variable. So for example, what we had in the warm-up was f of x equals x squared minus 2x minus 3. But maybe you don't like the letter x. Maybe it's a different question and a different letter's used. You could have f of t, where the input's t, but the same rules apply to whatever the input is, because this function f is the same for within one particular question or scenario. So this function is still doing the same thing to whatever input it's given. If you don't like t, how about capital Q? Or maybe z, and so on. But the general rule would still apply to all. So what we did for question 2 is we chose x minus 2 as our input. So this is just a recap of a warm-up in a way. What if we chose x minus 2 as our input instead of x? So just returning to the warm-up for a moment, here's a graph of f of x, which we had. So I've already talked about this. So that's f of x. And on the other side, we have f of x minus 2. And so f of x minus 2, you can see over here, what's happened is the whole graph of f of x gets shifted 2 units in the positive x direction. Okay, so everything we can see here gets moved 2 units along. Let's have a look at task A now. So task A, again, uses the same function, which we're going to call a parent function later, f of x, which is x squared minus 2x minus 3. So let's just remind ourselves of what we found out about this one previously. So this one, remember, can be factorized into x plus 1, x minus 3. And in completed square form, we worked out that this was x minus 1 all squared minus 4. And so before we actually go into question A, it doesn't ask you to do this, but I'm just doing it just for illustration purposes. I'm going to plot f of x anyway. And so f of x has a root at minus 1 and positive 3, and crosses the y-axis at minus 3, and has a minimum down here somewhere at minus 4. So if I just sketch in my version like this, so if I just call this now f of x, we can now have a look at how f of x plus 1 compares. So with f of x plus 1, all we're doing is swapping the input from x to being x plus 1. So instead of squaring x, we're going to square x plus 1. Instead of taking away 2 lots of x, we're going to be taking away 2 lots of x plus 1, and then minus 3, because minus 3 is invariant of x. Minus 3 is a constant, which doesn't depend on the input. So if we neaten this up, expand it all out, x plus 1 all squared is x squared plus 2x plus 1, minus 2 times x, that's minus 2x, Minus 2 times 1 is minus 2, then minus 3. So now this can be neatened up further. The positive 2x and the negative 2x, that cancels, and so we're just left with x squared plus 1 minus 2 minus 3. So 1 take 2 take 3, that's the same as minus 4. So we have x squared minus 4, which we can then factorise into x plus 2, x minus 2, because it's a difference of 2 squares. So it's going to have roots at positive 2 and negative 2. So if I just remind us of what f of x had for its intercepts, we had minus 1 and positive 3, and a y-axis interception at minus 3. Also as well, it had a minimum point at 1 minus 4, and so this here has a minimum at 1 minus 4. Expressing f of x plus 1 in completed square form, well, it already was here. So f of x plus 1 we worked out was x squared minus 4. You can think of this as x minus 0 all squared minus 4 if you like, just to see that the turning point of this one is going to be 0 minus 4. Okay, so this one here, I'm going to be plotting f of x plus 1 in red. So it's going to have a minimum at 0 minus 4 instead of 1 minus 4. Okay, it's going to have roots at minus 2 and plus 2. And its y-axis intercept, again, is minus 4. The y-axis intercept is the same as where it is at the turning point. So just to sketch this, if I can do. Going up there, and the same at the other side. Like so. So that's the graph of f of x plus 1 done. Remember from the warm-up, we did f of x and f of x minus 2. f of x minus 2 was a movement of f of x plus 2 units in the x direction. Now look at f of x plus 1. To go from f of x to f of x plus 1, compare these roots, compare these coordinates. We've actually moved f of x minus 1. So again, it looks that when the changes in these brackets, if it's a plus or minus number, the actual movement is opposite to what common sense might tell you. So f of x plus 1 doesn't move the x coordinates plus 1, it moves them minus 1 relative to the original f of x. So f of x plus 1, we move one x coordinate back. The x coordinates, we subtract 1 from them. Let's have a look at another example. Task B. Again for task B, I'm going to start by just putting in the exact same thing for f of x. Okay, so I'm not going to go through the same process of factorising it and explaining what the turning points are. I'm just going to write these on. So it was minus 1 and 3, and the turning point was at 1 minus 4. So just going to sketch on f of x. Like so. Label it f of x, and now we're going to compare what f of x plus 1 would look like. And so f of x plus 1, let's just do this algebraically. If you're thinking what might happen, and you turn out to be right, great, because the whole point of what we're going to do is arrive at the general concept, so we don't have to go through these algebraic steps all the time. But we're just going to prove to you why it works using the algebra. So f of x plus 1, we just take this whole thing here and add 1 to it. So that's going to be x squared minus 2x minus 2. Minus 3 plus 1. That gives us minus 2. So in completed square form, f of x plus 1, we take the x squared and make it an x. We half the minus 2, make it minus 1. We square that. We subtract off the minus 1 all squared. So subtract off minus 1, then minus 2. And so that gives us x minus 1 all squared minus 3. So just label on what we had from f of x, its roots, the y-axis intercept, and the minimum at 1 minus 4, and let's now compare that to f of x plus 1. So for f of x plus 1, we can see the minimum here is now at 1 minus 3 instead of 1 minus 4, and so the turning point, the minimum, is going to be 1 higher. Okay, so the turning point is going to be here. We're also asked as well to label all points of intersection with the coordinate axes. So this is a bit harder because this doesn't factorise. And so whereabouts is f of x plus 1 equal to 0? So we just set this expression here equal to 0. So we can do this here. So where is x squared minus 2x minus 2 equal to 0? What I'd suggest we do is use the completed square form. So let's say, when is x minus 1 squared minus 3 equal to 0? So if we add 3 to both sides, x minus 1 all squared needs to equal 3. Square root both sides, we get that x minus 1 must be root 3, but remember, incredibly importantly, plus or minus root 3. So therefore x, the roots are going to be either 1 minus root 3 or x equals 1 plus root 3. Okay, now I'm going to just suggest we work out what these are algebraically. Sorry, not algebraically, I mean numerically. So 1 minus root 3, what's that going to be? So 1 minus square root of 3, that's about minus 0.732. Okay, so it's not quite minus 1. So what's telling us here is that it's going to be somewhere about here. Okay. Likewise, 1 plus root 3, that's going to be 2.732, so close to 3, but not quite. It's going to be about here. So we can label these on. So we had 2.732, and minus 0.732. So could be something like this. And the same on the other side using the symmetry of quadratics. So I'm going to label this green one f of x plus 1 because it is. And so like we saw in the warm-up questions, f of x plus 1, the plus 1 is outside of the brackets of the f bit of the expression, so the plus 1 is on its own, and it works in a common sense way. We literally just add 1 to the whole curve. The whole curve of f of x goes up 1 unit. Okay, so the minimum goes up by 1. Every single point, in fact, goes up by 1. If it doesn't look like it does, it's not because it doesn't, it's because my sketch is pretty rubbish. My sketching ability is pants. But the whole curve goes up 1 unit. So let's see if we can generalize what we've got so far. So using the particular results, and these are just a few because from the warm-up and task A and task B, I've actually got quite a lot. So just picking out a few particular results. So let's have a look at these curves. So I've put in red f of x, I've put in green f of x plus 1, I've put in blue f of x plus 1 all in brackets, and all these coordinates relate to these different curves. So it's called the information overload. So what I'm going to do now is just colour code these coordinates to each of these curves so you can see clearer. Okay, so f of x is colour coded in red, f of x plus 1 all in brackets is colour coded in blue, f of x plus 1 is colour coded in green. So you can see here, for example, f of x plus 1, the corresponding coordinates are all 1 higher than f of x. So look at the minimum here, that's 1 higher. And for f of x plus 1, they're all 1 unit different, 1 unit backwards from f of x. So in terms of noticing this, have a look at minus 3, 0. Okay, that's 1 unit back, 2, 0 for f of x plus 1. Minus 1, 0 has become minus 2, 0. And likewise, a minimum of 1 minus 4 has now become 0 minus 4. So these are just particular results though, these aren't the general results. However, we can use our intuition to generalize it for when we're not just adding 1 or adding 5 or subtracting 2. What is it for just any general change in the original function f of x, if we're adding or subtracting a constant? So for our function, f of x equal x squared minus 2x minus 3, when we change the input of f of x from x to x minus 2, that translated the graph of f of x 2 units to the right. And so that minus 2 inside the brackets worked as a plus 2 for the x. Changing the input of f of x from x to x plus 1, when we looked at that, that plus 1 worked as a minus 1 in terms of the x coordinates got shifted 1 to the left. So in the brackets, it sort of works in an opposite to common sense way. Minus 2 with plus 2 to the right. Plus 1 means we minused 1 to the left. When we added 1 to the expression f of x to make f of x plus 1, that did actually shift the whole thing 1 unit up. So the plus 1 on the outside works in a common sense way and affects the y coordinates. So in plain English, when the change of f of x occurs inside these brackets here, it affects the x in an opposite to common sense way. When the change of f of x happens outside of the brackets, and we have a constant on its own, it affects the y coordinates in a common sense way. So next up, let's just generalize this to the graph of y equals f of x plus a, where a is any constant. Okay, so if we have f of x plus a, it's a translation of a graph of y equals f of x by the vector minus a, 0. In other words, if a was plus 2, this would be minus 2. So if it was f of x plus 2, that would move f of x 2 to the left. If a were negative, we'd move in a positive direction to the right. And so I've got a demonstration here to show you. So you might need to pause the video to make sense of it because it moves quite fast. But if you have a look at this clip here, which we've got from Desmos, f of x is fixed in red, f of x plus a is moving along in blue, and this variable a I'm changing on the slider. So as a becomes more negative, the graph goes over to the right. As a goes positive, like it is here, the graph is on the left, and so it shifts in the opposite direction to what you may expect. So that's for the change where we've got y of f brackets x plus some constant. Now let's consider how f of x can be translated to f of x, close brackets, plus some constant. In general, that's going to be a change in the y direction only by a units. So for example, if a were 5, if we had f of x plus 5, f of x moves 5 units up. If it was f of x plus 10, we'd move 10 units up. If it were f of x minus a million, we'd move a million units down. So this one works in a more common sense way. And likewise, as before, I've got a graphic to try and show this to you. And again, feel free to pause the video to digest it. This is moving a bit quicker. Okay, so as a is minus, the blue is below f of x. When a is positive, it's above the graph of f of x. And so this works in a more common sense way. So the general sort of plain English rough and ready rule is when the change is outside of the brackets, it affects y in an obvious way. When the change is inside the brackets, it affects x in the opposite way to what one may expect. Now we know that general pattern, the general rules, it really helps us to not get caught up in having to rearrange things with some awkward algebraic manipulation. So if we're given a parent function, and by parent function I don't mean it's a mum or dad or foster carer. What I mean by parent function is it's the original function we can then adapt without having to just rewrite the whole script. And so for this question, question 1, part 1, we've got f of x, which is x plus 2, brackets x minus 1 all squared. So to work out what f of x plus 1 would look like, we don't need to worry about actually sketching out anything brand new. We just look at f of x and adapt. So for f of x, let's just look at this. It's going to have roots at x equals minus 2, and when x is 1. Now 1 is going to be a repeated root because it's x minus 1 all squared. Okay, and we also know that it's going to be cubic. X times x squared, it's going to be a positive cubic. It's going to have this sort of characteristic shape. Okay, and as well as that, we also know that f of x plus 1, from what we mentioned before, that's going to shift this whole thing back 1 unit. And so f of x plus 1, the x coordinates, we're going to subtract 1 from each of them. So f of x plus 1 is going to have roots where x is minus 3, because it's 1 less than minus 2, and at 0. So it's going to have a repeated root at 0. So at the origin it's going to bounce, as it were. So we just need some axes to get going. Remember, this is only a sketch. So that's our x-axis and our y. So it's going to come up through minus 3, bounce at 0 and go back up again. So it's going to be something a bit like this. Okay, so just label on, that's minus 3. That's obviously 0, but we know that because that's the origin. We don't need to beat the examiner over the head. We can leave it at just minus 3 and we're good. We now have g of x to consider. So for g of x, which is 1 over x, we need to consider what g of x plus 1 would look like. For a moment, I just want to return to the previous lesson. This is a reciprocal graph. So we need to know almost offhand really what the characteristic shape of 1 over x looks like. So to remind you from the previous lesson, it's going to look something a bit like this. Okay, so there's a graph of 1 over x. As you can see, it's got asymptotes which are the x-axis, the horizontal asymptote, and the vertical asymptote is the y-axis. Now g of x plus 1, this plus 1 is outside the brackets, so all of this is going to be shifted up 1 unit. So the horizontal asymptote, which is where the x-axis is, that's going to be shifted up 1. So instead of the asymptote being where y is 0, the x-axis, the new asymptote for plus 1 is going to be at y equals 1. So you need to imagine this, but these red curves shifted up 1 unit in the y direction. So let's adapt this and think what we get. Okay, in fact, what I'm going to do, I'm going to leave this on. Just saves me having to redraw the whole thing. And so these red curves, that's g of x. Okay, so if I just write g of x, so g of x plus 1 is going to just be the whole thing but 1 higher. Okay, so we're going to have an asymptote here where y is equal to 1. So I'm going to label this on now. And the curve is still going to have the same vertical asymptote, but the horizontal one is going to be where y is equal to 1. I know it should have come down a bit steeper sooner, but I can't sketch very well, so please forgive me. And likewise this one's just going to go up 1 higher, so it's going to look something like this. And goes down, steeper, 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 approaching the y-axis very closely. And so this one is actually going to have a interception at the x-axis. I'm just going to label on that the blue one is g of x plus 1. So you can differentiate the red from the blue. And it does have an intersection with the x-axis here. So when a curve intercepts with the x-axis, that's when the function is equal to 0. And so at this point here, okay, that's when g of x plus 1 is equal to 0. So in other words, I'm saying that 1 over x plus 1 is equal to 0. So if we subtract that 1 from both sides, so 1 over x equals minus 1. You can rearrange further if you want to, like multiply both sides by x and whatever, but 1 divided by what number would give you minus 1? X has got to be minus 1, hasn't it, if you think about it? So that x-axis intercept is where x is minus 1. And that's all there is to it. But let's have a look at another example now. This one is where people really get confused by. Okay, this looks algebraically, so people often fall into the trap of trying to expand and manipulate and expand all this out and get really, really muddled. But actually, it's much simpler than that. So, to part A, first of all, we just need to sketch this graph here, which is y equals x cubed minus 2x squared minus 3x. Now, the first thing to note is this does factorise. So first of all, let's factorise out an x, and we get x squared minus 2x minus 3. So this bracket here factorises further. This bracket, we can say that's going to be the same as x plus 1 x minus 3. So therefore, we can see what the free roots are by just inspecting when this is going to be equal to 0. So roots are when x is 0 from this x here, when x is minus 1, or when x is 3. Also as well, we can see clearly this is going to be a cubic, so it's going to have the same general cubic characteristic shape like such. I always do this little flick at the end. I wish I didn't, but I don't know why. Anyway, it's going to have that sort of shape, and it's going to go through the origin as well, because when x is 0, this whole thing becomes 0. So we can sketch on, first of all, y equals x cubed minus 2x squared minus 3x. So let's do this here. So label on the x-axis and the y-axis, like a good student. There we go. And this one, now we know the roots are -1, the origin, and 3, we can sketch this on easily enough. So it's going to be something looking a bit like this. -1, 0, and 3. Not too bad for me, that. So label on this here. So that's -1, that's 0, and that's obviously 3. Now part B is where people get often very muddled. So part B, we've got this point with coordinates 1, 0. So whereabouts would 1, 0 be on our graph? Well, obviously it's going to be between 0 and 3. 1, 0 is going to be about here, isn't it, if you think about it? So 1, 0, that's here effectively. So it crosses the x-axis at 1. And what I'm going to do here now, I'm going to call this function f of x. That's some function of x. So going back to B now, if a point with coordinates 1, 0 lies on the curve with this equation here. And so this looks really awkward, doesn't it? But compare it to f of x. F of x, we've got something cubed, we have something cubed here. Take away 2 lots of something squared, we're taking away 2 lots of something squared here. And for f of x, it's -3 lots of something, we have -3 lots of something here. The only difference is, for f of x, the something is just x, here the something is x plus a. In other words, what I'm getting at is the input. Here, this is f of x, so our input is x. We're cubing the x, taking away 2 lots of this x squared, subtracting away 3 lots of x itself. Here, instead of an x, it's x plus a. So it's actually identical in one sense to f of x. The only difference is, for f of x, the input was x, dum dum dum. Here, because we've got x plus a, x plus a, x plus a, this thing here must therefore be f of x plus a. So, because the question has been worded in such a way, it's been a bit subtle, a bit sneaky, but all this question is really is a question about transforming graphs. So a is some constant, and there's 3 possible values of a. Okay, so all it's saying here is this new curve here, which is f of x plus a, it's basically a transformation of this blue one. Okay, it's saying, what could a be? Well, we need to think about this. There's 3 different cases. So one case is because f of x plus a is just a transformation of f of x. This blue curve here, it could be that -1 moves to 1. It could be a transformation like this. That would work, wouldn't it? So it could be the case that -1 moves to 1. So I'm going to write down the 3 separate cases. So case A could be that -1, 0 moves to 1, 0. And so one thing is, it could be that f of x is translated 2 to the right. That's one option. Another case, let's call this case B. Maybe it's not the -1 that moves to 1. It could be the origin moving. It could be we go from 0, 0 to 1, 0. I'll just show you this on the diagram. So it could be, instead of it being like this, it could be that the origin here just shifts 1 unit along like this. Okay, so that's another option. So it could be that 0, 0 moves 1 to the right. In other words, another possible transformation is that f of x, instead of moving 2 to the right, we could have the same effect where it just moves 1 to the right. The third case, these cases have been the graph moving forward. However, it could be that this root here, 3, moves 2 backwards like this. 3 could move 2 backwards to the 1. And that's the third option. So let's call that case C. Oops, change that to a black pen. So case C is that the point 3, 0 moves back to 1, 0. In other words, that's f of x translated 2 to the left. So now all we need to do is just remember what A needs to be in the 3 cases, moving 2 right, 1 to the right, or 2 to the left. Now, what I mentioned earlier, the sort of common sense way of looking at it, I think, is when the change happens in the brackets, which it has, the x in the brackets has changed to an x plus a. This change affects the x coordinates in an opposite to common sense way. So instead of adding a to the x coordinates, we subtract a. So if we're wanting to move it 2 to the right, plus 2, a must have been minus 2. So it must be from f of x to f of x minus 2. So one option is that a may have been minus 2. If a were minus 2, we'd add 2 to the x coordinates, and minus 1 would move to positive 1. Another option, if we wanted to move 1 right, if the origin moves to 1, if we wanted to move it positive 1 units, a would have to be negative 1. Or the final option, if we're moving 2 to the left, if we want to subtract 2 from the x coordinate to go from 3 to 1, a would have to be positive 2. So these are the 3 different options for a. Either a is minus 2, minus 1, or positive 2. And that is question 2 sorted. So question 2 could be quite awkward, but actually it's about this concept of transforming graphs and spotting when you can consider a question not as some beastly algebra, but in terms of a transformation as something familiar. Lastly, this worked example here, sketching translations of unfamiliar functions. Now by unfamiliar, we don't have any function to work with, we're just told this is f of x and deal with it. So even if we wanted to use algebra here, we couldn't, which in a way makes it simpler because you're forced into doing it in terms of transforming a graph. So let's have a look at this question. The diagram shows a sketch of a curve y equals f of x which passes through the origin 0. The points a, 1, 4, b, 3, 1 also lie on this curve. Sketch the following graphs in the boxes provided, indicating the positions of the translated points where it goes through the origin, a and b. So first of all, f of x plus 1. So before we try anything, let's just remind ourselves and think, what would f of x plus 1 do to f of x? The change has occurred inside the brackets, so it's going to affect the x coordinates in an opposite to common sense way. So the x coordinates, instead of adding 1 to them, we're going to take 1 away. So we're going to subtract 1 from each x value. We're going to essentially move the graph 1 unit to the left. Similarly for b, the change is in the brackets still. So instead of subtracting 2 from the x coordinates, we're going to add 2. So each x coordinate is going to grow 2 bigger. In other words, we're going to move the graph 2 units to the right. For C, a slight trick question here. we need to rearrange this by adding 1 to both sides. We want y equals f of x plus 1. So we're going to take the function of x and add 1 to the whole thing. This plus 1 is outside the brackets, so it affects y in a common sense way. We're going to add 1 to each of the y values. In other words, the whole graph is going to go 1 unit up. So these graphs aren't shrinking or being stretched, they're just literally moving. We're going to come on to shrinks and stretches in the next lesson. And so if I want to move this 1 unit to the left, we know it's going to have the same shape, so I'm just going to nick it from here. Jump. Okay, so it was here. Now it's just going to be 1 unit over, like that. And so 0, 0 is now moved to minus 1, 0. And so that's going to be minus 1. This maximum point was 1, 4. Okay, so 1 unit to left is going to be 0, 4. Whoops, I've totally messed this up, haven't I? I'll leave it there. Yeah, 1, 4 becomes 0, 4. And so this is going to have to go on the y-axis. Apologies, sort of didn't think ahead there, but you see it's easily done. But if you're on the ball, you can spot your mistakes and correct yourself, which luckily I've managed to do. Close call though. And so anyway, it's going to cross the x-axis. Instead of 0, 0, that's going to be 1, 0. Minus 1, 0, I mean to say. This point here is going to be now 0, 4. And this one here, 3, 1, is going to move 1 to the left. This point, this minimum, is now going to be 2, 1. For part B, we're going to move the whole thing 2 units to the right. So it was sort of like this. So I'm going to hop it along 2 units. So they're going to go 1, 2. Okay, so overlapping with that somewhat, so I'll just pop it here for now. As long as we label it clearly enough, it's okay. So 0, 0 is going to become 2, 0. So that's coordinate 2. That almost looks like a 3. I'm just going to correct that. There we go. This one is moved 2 units along in the x direction. So 1, 4 becomes 3, 4. And 3, 1 is going to become 5, 1 because of 3 is moved 2 units along in the x direction. The last one, part C, where we move the whole thing up. In fact, I'm just going to label these A, B, and C so we know which ones we're talking about. We just need to move this whole graph up for part C. So that's y equals f of x plus 2. And C we had y equals f of x plus 1. So we just need to move the whole thing up 1 unit. So it was here-ish. So the whole thing goes 1 unit up, like so. That was at the origin. If it moves 1 unit up, it's now going to be at 0, 1. So that y-axis intercept is now 1. This local maximum, instead of being 1, 4, that's going to grow now to 1, 5. And 3, 1, that 1's going to grow 1 and become 2. 1 plus 1 is 2. So this point here is now 3, 2. And then we're done. So now it's over to you. If you could have a look now in your spare time, page 74, exercise 4E in the blue algebra book, questions 4 through to question 12, and also page 80, exercise 4G, questions 1, A, B, and C, and questions 2, A, B, and D. So it's a bit of work to get your heads around, but it's worth it, it's valuable, in fact it's essential for the A level, this particular exercise, as most are in fairness. So have a go at those questions, let me know if you get stuck, self-assess using the answers at the back, don't just plug away hoping that you're getting it right by chance. So keep working hard, I'll see you again soon I hope, take care of yourselves, and bye for now.